All right. So section 13 is triangle congruences. We've taken a look already at, I believe it was side, angle, side. And we've shown congruences using this. But this is because, right, we assumed side, angle, side because it's an axiom. The rest of these, the remaining theorems can be proven using side, angle, side, or previous theorems. So the first one that we approach, angle, side, angle, there's only two ways that we could prove it. We could either prove that every angle is congruent and that every side is congruent, which would give us the definition of congruence, or we can use the side, angle, side axiom. So we'll use the side, angle, side axiom to help us out in both of these, or for several of these. So the angle, side, angle, triangle congruence condition. If we have two triangles such that we have an angle that is congruent followed by a side, sides that are congruent, line segments, and an angle that is congruent, so we have side, angle, side in that order, angle, side, angle in that order, then we have that the two triangles are congruent. Well, excellent, that's fantastic. So how, well, let's go ahead and prove it. It takes several steps, but what we're going to do is we're going to use the side, angle, side to help us prove it. So we've got a couple of options, right? Since we have the side AB, we could also consider the side BC, or we could consider the side AC. So show that this guy is congruent to this one, or that this side is congruent to that one. We've got a couple options. All right, so I'm going to get rid of those for now. And what we're going to do is we're going to choose the side AC. So we'll begin by stating what's given, as we should do. So we've got the given conditions. Let's see here. This does fit halfway decently on here as long as I don't write too big, which sometimes happens on this computer for some reason. So we've got the three givens. AB is congruent to DE. We have that angle A is congruent to angle D. And we have that angle B is congruent to angle E. So these are simply what's given. That's easy enough. Now what we want to do is we want to show that AC is congruent to DE, and then we would be able to simply use side, let's see here, side, angle, and then the side to conclude that the two triangles are congruent. And we're going to do that by a contradiction. So we want to suppose that the side DF is in fact shorter than AC. Okay, so this distance DF is shorter than the distance AC, which would mean they're not congruent. So we're going to, this is an assumption for a contradiction. Now, when we get to our contradiction, right, when we get to this statement that says something different, we're going to conclude that DF must not be less than AC. But if DF is not less than AC, technically, what does that allow us to conclude? You know, bare bones, not much thought into it. If DF is not less than AC, what is DF? It must be, what is that? Not right. So that's what we want to conclude. But in reality, if I were to take it, if DF is not less than, if it's not less than we want to give what it should be. We want it to be equal, but the fact that it's not less than, does that actually mean that it is equal? No, that means that it's actually greater than or equal. So this doesn't give us congruence, right? Equality gives us congruence. However, if we compare AC, right, if we find that AC, if we find that DF is greater than AC, right, we would be able to do the exact same work by beginning the assumption that DF is larger than AC and finding a contradiction that DF is less than AC. So we can actually do this both ways, and because technically they're the same triangle, or we're going to find that they are, we would actually have that we could swap this. So when we do the one way, when we show that DF is actually greater than or equal to, we're actually simultaneously showing that AC is less than or equal to, or is greater than or equal to as well. So we get the equality even though we only showed the inequality one direction. So we get equality even though we only showed inequality one direction. All right, and that's something that's kind of glossed over in this proof. So that would be an example of something that I could ask you on an exam. Why could we conclude this? Shouldn't this have been the conclusion? Okay. So suppose here that DF is less than AC. Of course, we're assuming that for a contradiction, as is stated in our nice two-column proof. So for number 3, the third step, all right, there exists a point. There exists a point, a unique point on AC such that AX is equal to DF. So that looks kind of weird right now, but if DF is shorter, then somewhere along here, if we place the point X, we're going to have that AX is equal to DF. Okay, so if that's the case, let's add in a line here. So we get this nice looking triangle. Okay, so if AX is congruent to DF, then what we have is triangle BAX is congruent to triangle EDF. Because we would have side angle, side angle, side angle, side angle, side. Excellent. So this is given by, right, we can actually say this because of, what is that? The ruler postulate. All right, so the next step is exactly what we said. Triangle ABX is congruent to triangle DEF. And this is given by side, angle, side, looking at side AB, this guy, and then the angle that we're interested in is angle A. So 1A, 1B, and then 3. There we go. Excellent. So that tells us that the measure of angle ABX is congruent to, or is, sorry, the measure is equal to the measure of angle DEF. Yes, DEF. And that is because of the definition of congruent triangles. All right. That tells us, well, that makes sense, but that's for a different reason. 3 into 2. Am I skipping this? What did I do here? Oh, that makes sense. AX is less than AC, but that makes absolute sense. 3 into 2. Oh, okay. Yep. It makes absolute sense, and we would think of that because of the line segment addition theorem. No, I'd have to look at the theorem, right? If we take a line segment and we have something in between, then the distance from here to there is less than the distance from here to here. However, we never actually said that this point is between, right? We never actually said that X is between A and C. We never actually said that. So what we need to use to recognize that this distance is less than that one is the combination of, let's see here, line 2, where DF is less than AC, and line 3, where we have that AX is equal to DF, giving us AX is less than AC. Excellent. So while we think that this would be obvious, it does require the justification, and by we, I mean myself, right? We want to make sure we justify everything. So this is simply a substitution of line 3 into line 2. Okay. So the next step, once we have this does give us that theorem that I was talking about earlier, which is the betweenness inequality. So we have that X is between A and C. And again, that is the betweenness inequality. Okay. And again, I wrote bigger, so I've got less space than I thought I would. Let's see here. The 8th step. The measure of angle ABX is less than the measure of angle ABC. ABX is less than ABC, and that is given by the angle interior inequality. X is in the interior of angle ABC, so the angle ABX must be less than the angle ABC. Angle interior inequality. All right, so we have at the same time that the measure of angle ABX is equal to the measure of angle DEF. So we can make that substitution in line 8. So ABX is replaced with DEF. Measure of angle DEF is less than the measure of angle ABC. And that was a substitution of line 5 into line 8. So we assumed that angle ABC and angle DEF are the same. So when we created this other triangle and said that it is congruent to this one, right, this angle that we didn't use got messed up. And since it got messed up, we're saying that this angle is actually the same as this angle, but it's not. We can see that. They're not the same. So this is the contradiction that we've arrived at. So this is exactly a contradiction. These two is assumed that they are equal to one another. So that is line 1C and line 9, the previous line. All right, 2 more things to say here, so we got just enough room. Step 11. With the contradiction, we assume, right, when we assume that DF is less than AC, we go ahead and say, well, that assumption was wrong, and so we conclude the opposite, that DF is greater than or equal to AC. But it's the exact same work to show that DF is less than or equal to AC. So we get the equality immediately, and we say that DF is equal to AC. That's lines 2, where we assumed for a contradiction, and line 10, where we obtained the contradiction. And then the 12th line, with DF equal to AC, we actually have side angle side, so the triangles, triangle ABC is congruent. ABC is congruent, there we go, to triangle DEF. And that is by side angle side using side angle, so 1A, 1B, and 11. Excellent. And that's what we wanted to show, that the two triangles are congruent to one another. So we have proved that when we have angle side angle, the two triangles are congruent to one another. Excellent. So this is an example, right? This is a little bit different for us. We don't see too many of these. So let's take a look at an example. In here, in this triangle, triangle APQ, or well, there's a million triangles here. So look at these triangles. If we have that the line segment from A to C bisects the angle PAQ, so that tells us that angle 3 and 4 are equal to one another, but we can't immediately use it. We have to state it and cite the definition of an angle bisector. And we want to, and we also have that angle 1 and 2 are congruent to one another. And we want to prove that PA is equal to QA. So we have some things that I'll try to highlight on the diagram. Because this line segment bisects the angle PAQ, we know that angle 3 and 4 are the same. So maybe we could actually put this kind of a mark there. Okay. We are given that angles 1 and 2 are congruent to one another as well. But those don't necessarily give us anything about any triangles that have AP and AQ. So I want to use congruent to triangles to show that they're the same. And I can do that. Notice that, of course, this side from the segment from A to B is congruent to itself. So we have an angle side, and then because this angle and this one form a linear pair, right, we can use the appropriate postulate, name off the top of my head, I don't remember. But then we can say that we know this angle, so we have angle side angle. Those two are also congruent by the supplementary postulate. No, not postulate, theorem. That one is a theorem. And then we have side angle side, or angle side angle. Yep. Angle side angle. So that's what we want to do. That's the approach we want to take. So proof. We have several things given to us. Again, line segment AC bisects the angle PAQ. And we also have that angle 1 is congruent to angle 2. And these are simply given to us. All right. Again, we know that angle 3 and 4 are congruent to one another. And that is because of the definition of an angle bisector. So we can say that angle 3 is congruent to angle 4 because of the definition of angle bisector. Definition of angle bisector. And then our next step, we'd like to say that, let's see here. Yes, okay. It still takes a couple of steps for us to get that these two are congruent to one another. But we want to talk about this angle, angle 1, and angle ABP or PBA, and angle 2 and QBA. All right, so we have that angle 1 along with angle PBA are supplementary. Angle 2 and angle QBA are also supplementary. And this one is a postulate. So it's the supplemental angles postulate or something of that sort. Supplemental postulate. Supplementary angle postulate. Refer to notes if more accuracy is desired. This is fine. For the fourth step, Rick, once we have this, when we have that an angle is supplementary with another angle, and that angle is congruent to another angle, and we have that angle is supplementary to this one, then we get that these two angles are congruent. And that is from the supplementary angles theorem. There we go. So angle PBA is congruent to angle QBA, and that is from the supplementary angles theorem. Okay, excellent. So we have that these two angles are congruent. We have that these two angles are congruent. We just need to state that this side is congruent to itself, or that segment is. So our fifth step is that AB is congruent to itself. And this is because of the reflexive property of congruence. Since congruence is an equivalence relation, it is reflexive, which means everything is related to itself. It is symmetric, so if AB is congruent to HI, then HI is congruent to AB, and then transitivity as well. Six, so we have side angle side, which means that we can say that triangles PBA and triangle QBA are congruent. And that side, oh sorry, angle side angle. Angle side angle, sorry about that. And that was this angle, this side, this angle. And we're given that here in, let's see, angle. So 3 is congruent to 4, side, and angle. So 1B, side is 5, and angle is 4. There we go. Oh, and it's, sorry, it's not that one, it was 2. There we go. 2 is where we said that these two are congruent. 3 and 4. Excellent. Okay, so what does that do us? Well, that gets us that this side and this side must be congruent because we have congruent triangles. So let's see here. AP is congruent to AQ. AP is congruent to AQ. And that is by the definition of congruent triangles. Excellent, we're done. Indicate the end of the proof. So showing that AP is congruent to AQ is the same thing as showing that PA is equal to QA. So that's sufficient. If you wanted to take this one step further and say step 8 is that AP is equal to QA, PA is equal to QA, order doesn't matter there. That's fine. So do as you feel necessary there, but this is fine. Okay. So we've done a lot of proving already, or at least it feels like it. Both of those have been a medium length for this one and kind of long for this one. So we've done quite a bit with just proofs so far. So quite conveniently, there are a couple of proofs that are given. They're all written out here. And what I'd like to do is, rather than discussing these proofs during lecture, what I'd like to give you the opportunity to do, because you do need this skill of reading the proof and understanding it on your own without explanations. So what I'd like to let you read through that. It saves us a little bit of time during lecture right now and gives you the opportunity to practice reading for understanding in a proof. So that'll be good practice for the exam, okay? So the angle side triangle congruence condition, right? Our theorem here, if we have angle side, then what we get is congruence. So angle side is fine. We like that. All right. As it states here, the proof is really similar to angle side angle, so it shouldn't look too much different than what we've already done, and that's one of the reasons that we won't discuss it. All right, so we haven't quite discussed all of our congruences, but we have talked about a few of them. So I want to write in here what our possible congruences are. So let's use black would be good, I suppose. We've got a few options on what combinations we can have. So we have side, 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 which we haven't talked about yet, but we will. We have side, side angle, which is what we're about to talk about now. We have side angle side, which is what we started off with. So we know that that one works. So I'm just looking at what are all the possible combinations, right? So there's three. If we're choosing three of them, what can we come up with? So side, 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 side angle, side angle, side. And how I'm generating this list is in a binary way. So if you're familiar with counting in binary, you can think of the S's as zeros and the A's as 1. So then you would have 0, 0, 0, 0, 0, 1, 1, 0, 1, 0. So counting in binary. But unfortunately, let's see here, slide it. Oh, the next one isn't too bad. SAA. So side angle angle, which is angle angle side, and that's the one we just looked at, so we know that that one is good. But then when we get to the next one, we would have, I'm just going to do it. Okay, so it would be angle side side, but this is the same as but this is the same as, parentheses here, come on now, side angle. So we've already talked about, or no, we're about to talk about that. That's what it is. And then we also have angle, side, angle, which we did just talk about before angle, angle, side. And the angle, angle, side was very brief, right? It was, hey, this is it. Did I even say it, or did I just talk about the proof? Maybe I didn't even say it. No, I said it. Angle, 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 side. Yeah, it was just very brief, right? We have the situation, don't forget about it. We didn't spend a lot of time talking about it. Okay, and then we have angle, side, angle, which we talked about before, angle, angle, side. And then we have angle, angle, side, which is the same as already given SAA. And I must be using a different font size here because this fit okay when I wrote it up the first time. There we go. And then all A's. There we go. Okay, awesome. So those are our possibilities. So we've already seen that we're about to see about side angle. We're going to see about side later. Side, angle, side, we know that we do have congruence there. Oh, come on now, did I get... There we go. Side, angle, side, so yes, that produces a congruence. Side, angle, angle, which is angle, angle, side. Yes, we already saw that. Angle, side, side, we're about to see in a moment. Angle, side, angle, we know that that produces a congruence. Angle, angle, side. Yes, wait, no, we're about to look at it. No, that's not the one we're about to look at. Oh man, they're so confusing. I got this. Angle, angle, side, we looked at that one earlier, angle, angle, side, so of course we get yes because it's the same thing as the answer over here, and then angle, 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 we'll also take a look at in a moment. Okay. So for side angle, let's say we have a side, and an angle. The thing about this is the angle here at B, I can change this angle. If I were to consider this side here to be on a hinge, essentially, then I would be able to let that rotate, and here again it would drop down below this bottom line, and then it would come back up to it, and then by allowing that movement, we get this image. So these two triangles satisfy side angle, but they are not congruent. All right. So side angle, no. Can't use that one as a justification for congruence. All right, now what about, so that takes care of everything but side, and angle. For angle, of course, what we can do is we can consider geometric shapes which are similar to one another. So triangles in particular we're concerned about that are similar to one another. So I can scale them, get my scaling factor, and I can produce two triangles with the same angles but with different side lengths. So definitely not congruent. So no. So the only thing that remains is side, which we won't talk about until I think a couple of pages yet. Okay, for now, just these comments on false congruences and a couple other random theorems. So the hypotenuse leg triangle congruence theorem. Here, what we want to do is, if we take two triangles, A, B, C, and D, E, F, if we assume that these two angles are right angles, and we have that AB is congruent to DE, AB congruent to DE, and BC is congruent to EF, BC is congruent to EF, then these two triangles are in fact congruent to one another. But hey, question, isn't this just side angle? Side angle? And didn't we just say that that's not true? Well, in this case, it is. Here, when we looked at side angle, we allowed that high point to, we allowed that side to rotate or to move, and it came back up and hit again over here. If we were to do that with this one, allow it to drop down, the next time that C comes up would be all the way over here, and so the new triangle we would have is this one. This would still be a right angle, and this side length would still be the same. But because this is a vertical line, right, because this angle is 90 degrees, we actually get that this angle measurement and this one are the same. So we end up with two triangles that are actually congruent to one another by doing that. Excellent. Again, I'm going to encourage you to read through that proof. This one is even longer than what we've seen before, 16 steps there. So feel free to read through that. If you have any questions, please bring them on Thursday, or send me an email, that would be fine as well. All right, so this theorem, the next theorem, is called the the inverse of the isosceles triangle theorem. So this gets into some inequalities for us. So the inverse of the isosceles triangle theorem. Actually, if it's okay with you, I'm going to really quickly see if I can go back and find the isosceles triangle theorem. And in fact, Control-Shift-F, I don't know how to spell this word, isosceles. Yep, there we go, triangle theorem. All right, so here we are. Okay, excellent. So the isosceles triangle theorem says that the two sides of a triangle are congruent if and only if the opposite angles are also congruent. Okay, so let's get rid of that. So we can, I just wanted to see what that said. So let's go back to page 74. If we have that two side lengths are not equal, then what we get is that yes, here we are. Of course, the angles are not equal either. So for triangle PQR, if PQ is larger than RQ, or that's true if and only if the measure of angle R is less than the measure of angle P. Now that's kind of hard to think of without a visual aid, so that we can do. Let's go ahead and look at triangle PQR, and I'm going to grab PQR. That works for me. Yep, excellent. We'll end up coming in with another line eventually. But if we call this P, Q, and R, maybe I didn't emphasize it enough, but no, and in fact, I probably drew this a little bit wrong. Let's do this a little bit differently. I need PQ to be longer. Oh, that was already longer than RQ. Oh man. Here I am changing things that didn't even need to be changed. Yeah, that seems, okay, yeah, so I think that's clear enough that PQ is longer than RQ. PQ is longer than RQ. Okay, excellent. So the measure of angle R is smaller, is not smaller than the angle of measure of angle P. I have that backwards. That's not what I want to get rid of. Put that back. Just get rid of this. Measure of angle R is greater than the measure of angle P. Okay, well, at least we have it copied down correctly now, and we were able to identify that with our visual aid, so that's excellent. Okay. Visual aids are nice for understanding and even correction, I guess, when we make mistakes there, but they aren't justification themselves. So we'll go ahead and do at least the forward implication of the proof. So we're going to assume that PQ is larger than RQ and show that this inequality holds for the angle measures. So this is a prose proof, so it's not the two column, so that things aren't numbered here. So assume that PQ is in fact larger than RQ as in the image above. And if that's the case, then we can subtract RQ from both sides. So PQ minus RQ is greater than 0. Okay, but we'll get to use that a little bit later. So let's go ahead and let X, it's a capital X, so it looks like the Roman numeral 10. Wanted to make sure capital was clear. So let X lie on QR, the ray QR, such that now R is between Q and X, so Q, R, X, and we have that the distance from R to X is equal to PQ minus RQ, which is possible because of the ruler postulate. So what I'm doing here is I'm making an isosceles triangle. I'm making it so that way from P to Q and from Q to X are going to be the same. So this thing that I'm adding on is a difference between PQ and QR. All right, so let's add our point X out here somewhere. I'm going to go ahead and stretch out that line, or maybe not quite that far. That looks to be about this. No, that's about the same. Close enough. So I'll put the X over here. And then I want to talk about the isosceles triangle PQX. All right. Then the distance from Q to X, that hardly looks like a Q, Q to X is equal to QR plus RX, which of course is equal to PQ minus RQ plus QR. So the QR I wrote at the end, and RX is PQ minus RQ. Cancellations, this is just PQ. Awesome, as we stated that we wanted. So we can say, thus triangle PQX is isosceles. PQX PQX is isosceles. All right, so since PQX is isosceles, I can make a few statements. Let me make those statements. Three things. The measure of angle QPX is equal to the measure of angle X. QPX, right? This one here is congruent to this one. So the measures are the same. All right, so then let's label a couple of angles in here. Call this one from the original triangle, angle 1, and this one from the original triangle, angle 2. And we can conclude that the measure of angle 2 is larger than the measure of angle at X because of the exterior angle theorem. Whew. All right, and then we can also say that the measure of angle 1 is less than the measure of angle QPX because of the interior angle-interior inequality. Yes. Okay, so to say those again, measure of angle 2 is greater than the measure of angle X, and the measure of angle 1 is less than the measure of angle QPX. The first line is just because it's an isosceles triangle, or the isosceles triangle theorem. The second one is because of the exterior angle inequality. And the third one is because of the angle interior inequality. Now with these equalities and inequalities, I come up with a nice string. So we have the measure of angle 2 is larger than the measure of angle X, which is equal to the measure of angle QPX. So I started with the middle line. Measure of angle X is equal to the measure of angle QPX. And then the measure of angle QPX is larger than the measure of angle 1. No, I wrote angle backwards. Measure of angle 1. That is, measure of angle 2 is larger than the measure of angle 1. Which is exactly what we wanted to show for the forward direction. All right. So that's the forward direction done. We do actually have the reverse direction available to us. Let me double check this here a second. So for the reverse direction, we assume the opposite. We assume that the measure of angle R is greater than the measure of angle P. I assume this part, measure of angle R, is greater than measure of angle P. We even copied it correctly this time. That's fantastic. Okay, so if that were true, all right, when we assume that's true, we can break this down into just a couple of scenarios. So we want to conclude that PQ is larger than RQ. So if we were to, the only other situations are that PQ is less than RQ or they're equal. So we can briefly state a couple of contradictions. So if PQ were equal to RQ, then the measure of angle R would in fact be equal to the measure of angle P. But this can't happen, okay? Or that would provide a contradiction, rather. And if PQ were less than RQ, then we would have that the measure of angle P was greater than the measure of angle R. Because that's exactly what we proved in the forward direction. But this provides a contradiction to our assumption, our actual assume. We're assuming that thing is true. Thus, it must be the fact that PQ is indeed greater than RQ. And that's it. Okay. We've got about 15 minutes left. And we still have like 3 pages of this section. Yeah, this is a long section. So we're going to finish this section on Thursday. What I'd like to do, since we do have 15 minutes left, is we'll take a look at this theorem, and maybe we'll try to get to the end of this page. Okay, I probably have been talking more than I need to, so I apologize. But hopefully it's been enjoyable to listen and watch. Okay, so the triangle inequality. If we are given some triangle ABC, then what we have is that the sum of the lengths of 2 sides is greater than the length of the third side. And that's all that this theorem states. Side length AB plus side length BC is greater than side length AC. Which I think is pretty straightforward in terms of understanding what that's trying to say. The proof is of medium length, and I'm almost certain that I'm not going to be able to fit it on this open space, so I'm actually going to start all the way up here at the top of the page. So our first step is make the assumptions, right? We're given triangle ABC. This is given. The next step, there exists a unique point, call it P, on the ray from A to B, such that we have P is beyond B, and that BP the length from B to P is equal to the length from B to C. Now this might not make a whole lot of sense. This doesn't look very good right now. It's because of the ruler postulate that we can do this, but let's draw a triangle so we can see what's going on here. So if we're given A to B, and then B to C, So let's say we've got this triangle here, and we have A, B, C. What we want to do is we want to extend this line out far enough that this side length and that side length are the same. That's what we're saying here. So this gives us, oh, I need the pencil, not the eraser. This is the point P. And then with this side length and this side length being the same, we have an isosceles triangle. So let's add in that one additional side. So that we can recognize our triangle. So this side length and that side length are the same. So the measure of angle 1 is equal to the measure at angle P, or the measure at P. So the measure of angle 1 is equal to the measure of angle P, and that's because of the isosceles triangle theorem. And the measure of angle 1 is less than the measure of angle ACP, and that's because we know that side length from A to P is longer than the side length from, no, what was it? Measure of angle 1 is less than A. Oh, no, okay, sorry. B is in the interior of angle ACP. So interior angle inequality. All right, and then since measure of angle 1 is equal to the measure of angle P, we can say that the measure of angle P has the same condition. And that's by substitution of line 3 into line 4. So because we have this inequality of angles, we come to an inequality of side lengths given by the previous theorem. So side AP is larger than side AC. So this is smaller than this. So since this one is smaller, this side length must be smaller than that one. Okay, so that makes sense. That's by the previous theorem, the inverse isosceles triangle theorem. So let's see here. We recognize, or we want to end up with an additional inequality. So, right, because that's what we're trying to end up with is this inequality here. But we have, right, so we have that A to P is larger than A to C, but BP is the same as BC. So we want to replace AP with AB plus BC, but we need to be able to make that substitution. So once we have that, so now we have this, we can use AP is equal to AB plus BP because of the segment addition theorem. With this, we can substitute, right? BC is equal to BP, so AP is equal to AB plus BC. This is the substitution that we want to put into line 6, and this one is itself a substitution. where we took line 2 and plugged it into line 7. And then the last step is to make that substitution that we want, replace AP in this inequality. So we will have AB plus BC is greater than AC by substituting line 8 into line 6. And that is exactly what we wanted to show. Yay! A little long, but not too bad. All right, so let's try and just finish up this page. So that way, when we meet next time, we can talk about the more on perpendicular lines. So the Hinge theorem says that if we have two triangles ABC and DEF, if AB is equal to DE and AC is equal to DF, but the measure at angle A is less than, or sorry, is greater than the measure at D, measure at A is larger than D, then we would also get, well, I didn't write down what it's supposed to be, but I'm pretty sure I know it's supposed to go there. Then this side length has to be longer than that side length. So BC must be greater than EF. All right. And then we can finally conclude with the side theorem. So if we have congruent sides, we have congruent triangles. Easy enough. Right? I believe this one should be a result of the triangle inequality and the Hinge theorem. You should be able to use to prove this. Right, the placement, maybe this one as well or instead, but it should essentially just be a result of theorem 13.5, 13.6, and 13.7 that give us this one. Otherwise, why would we have placed this one here? So makes sense. Anyway. So this is hardly early. It is technically, but 5 minutes before class officially ends. So thank you for your attention. And we'll see you guys on Thursday.